So in this video, we're going to introduce the idea of the definite integral. So if we step back to the previous two homework assignments, we identified in the last two assignments that we could estimate the area under a curve using rectangles. So what we did is we said, hey, let our function be continuous and non-negative. So our function needed to be above our function needed to not be below the x-axis. So if we had a continuous non-negative function over a closed interval from a to b, we estimated the area under the curve by adding up the area of estimating rectangles. Then what we did in the last homework assignment, we said, hey, we can take this estimate for the area under the curve, which we call a Riemann sum, and we can get the exact area if we take the limit as the number of rectangles we use for our estimate, if we take the limit as that number goes to infinity. So what we want to do now is define the definite integral. And the only thing we're going to change relative to the previous two homework assignments is we're going to eliminate the requirement that the function be non-negative. We're going to say, hey, it's okay for the function to be below the x-axis. So we're going to let our function outputs either be positive or negative. We're going to allow that function f of x to be above or below the x-axis. And then instead of an area under a curve, we're going to talk about the signed area under the curve. So if our estimating rectangles are above the x-axis, we get positive area. And that will be because our function f evaluated at any c on an interval is going to be positive, and we get a positive function output times a width gives a positive area. But if the function goes below the x-axis, our function values f are going to be negative, so we'll get a negative number times a width gives us a negative area. And we're going to allow ourselves to take the sum of the positive and the negative areas, and we're going to call that summation, when we allow the function to be negative, we're going to call this a definite integral. So again, it's area under the curve, but now the area could potentially be negative. We could be adding the sum of positive and negative area. And in calculus, when we have a signed area, we want to calculate a signed area, we represent it with the definite integral symbol. So the idea is if we want to take the limit as the number of estimating rectangles goes to infinity of the function times delta x, then we represent that summation using the antiderivative symbol. So this is going to look exactly like the antiderivative symbol from the antiderivative homework. The only difference in that homework is we didn't have a number at the top and bottom of the integral symbol. So you're going to use the antiderivative symbol. Here's the function. Here's the function. As n goes to infinity, delta x goes to 0. So instead of writing delta x, we write dx. And summation, we use this style of s to represent the summation. So this is the definite integral, and note that it's a and b right here. Those are just corresponding to the lower and upper bounds over which you're doing the summation. So bottom line is definite integral means find the signed area under the curve. So we're not requiring the function to be always positive. If the function is positive, then we're getting the positive area under the curve. We're getting the area between the function and the x-axis, and because we're allowing f of x to be above or below the axis, we have the potential of getting negative area. We represent the definite integral with the symbol. So if you see this symbol, this is really telling you to find the signed area under the curve. It's that straightforward. Find the area.